Okay, let's talk a little bit about Friedel-Crafts alkylation. So we talked last time in the introduction to electrophilic aromatic substitution, as well as what we talked about in class on Thursday. And we learned that what we have here is a class of reactions where the benzene ring is acting like a nucleophile and it's attacking some sort of electrophile, which connects one of the carbons in the benzene ring to that electrophile. And then it finally ends with the deprotonation of the proton that's on that carbon that's now connected to that electrophile. And by deprotonating it, you bring the ring back to aromaticity. You reform the double bond that was used to attack as a nucleophile some electrophile, if you recall. And that's what we're going to see is going to happen here with Friedel-Crafts alkylation. In this case, there's always an electrophile and there's always a catalyst for the most part, because once again, we're dealing with benzene that even though it can act like a nucleophile, it's got that aromatic stabilization that it doesn't want to lose the aromaticity. So it doesn't really want to act like a nucleophile. So you have to make the electrophile more electrophilic. And we do that by adding these acid catalysts that they really help stimulate the electrophilicity of the carbon. And what we see here is that the catalyst used here, very similar to the catalyst we've seen so far, at least for bromination, is a trihalide metal compound. In this case, it's aluminum chloride that's being used. But it's a very similar mechanism to bromination or chlorination, in which the chlorine atom is drawn towards the metal center of that trihalogen metal complex. And one of the lone pairs is drawn into it, which makes the chlorine have a positive charge once it forms that bond connection to the metal, which then strips the electrons that the chlorine once had to the carbon atom it was connected to off the carbon atom, turning the carbon atom into a carbocation. And that carbocation is the electrophile that's now going to be attacked by the benzene ring. We've also formed that tetrahalide metal complex that we saw in bromination chlorination. Once again, the mechanism, as we're going to see over and over again for electrophilic aromatic substitutions, these 5 reactions, I think, Friedel-Crafts alkylation, acylation, bromination or chlorination, sulfonation, and nitration, about 5 reactions. The mechanism is pretty much the same, other than the formation of the electrophile, whatever step or steps that's involved in that, that's unique typically to those different types. But for all these EAS reactions, the main part of it is the same. The benzene ring as a nucleophile attacks the electrophilic site, which makes a connection between one of the carbons in the benzene ring and the carbocation, or not always the carbocation, but the electrophilic atom in your electrophile, which removes aromaticity, but there's still some stabilization of the carbocation. There's still some resonance, which, although it still is a pretty high energy complex, the sigma complex, it's a high energy intermediate, it still can exist. And then what happens is once you do form that, the next step is a proton transfer where you deprotonate the carbon that is now connected to the electrophile. You deprotonate that proton that was once there. And by doing that, you bring it back to aromaticity with essentially one of the hydrogens on the benzene ring is now substituted for whatever the electrophile was. Once again, very similar to bromination, nitration, and sulfonation that we learned about on Thursday's lecture. Now, there's a couple issues we want to talk about with Friedel-Crafts alkylation. The first one is it works splendidly with simple, small primary halides, alkyl halides. So ethyl chloride, methyl chloride, the methyls and ethyls, or using the IUPAC nomenclature, chloromethane or chloroethane. Those alkyl halides work wonderful with Friedel-Crafts alkylation. The catalyst grabs onto the chlorine. Now, for these smaller ones, primary carbocations don't like to exist. So even though it will undergo Friedel-Crafts alkylation, these ethyl and methyl halides, particularly chloride, I should say, it doesn't form the carbocation. Rather, it forms this complex structure. It stays in this complex structure, and this carbon is then attacked by the benzene ring, as part of this complex. And in doing that, or when that happens, I should say, you would have the benzene ring attack the carbon as the chlorine finally lets go. So you never really form a carbocation intermediate electrophile. Instead, it's sort of an SN2 process where the nucleophile attacks as the leaving group falls off, the leaving group being this chlorine that's now part of this complex structure here. Now, while it works well with those smaller ones, particularly ethyl and methyl chloride, or chloroethane and chloromethane, it doesn't work as well for these larger alkyl halide, primary alkyl halides. So chloromethane, chlorobutane, etc. When it's 1-chlorobutane, when it's the primary halide. And the reason why is because if you think back to our discussions about electrophiles, particularly carbocations back in OChem 1, when you try to form a carbocation, the carbocations are typically susceptible to carbocation rearrangement. And actually, even though it doesn't, the carbocation doesn't form first, what we find is when you've set up this possibility for a primary carbocation to form, what ends up happening is the leaving group can fall off in the course of a carbocation rearrangement event. That is to say, either a hydride or methide or even larger alkyl group shifting over so that a more stable carbocation, say a secondary or even a tertiary carbocation, can form. So you have to watch out for that. You have to think, okay, where's my positive charge going to be forming at? Oh, it's a primary carbon. Okay, well, is that primary carbon rearrangeable? And it is, in these larger structures here, there's this hydrogen here that can shift over, and that's what we see happens. It shifts over, so a secondary carbocation can form as the tetrachloroaluminum complex falls off. So when you can form it, and you're only looking at the immediate neighbor carbon or carbons. So you don't look at something 2 carbons or 3 carbons away. That's why the ethyl doesn't really shift, because if you look at the ethyl chloride, or we only down here, even if you tried to shift this over here, like one of these, it's still going to be the same exact primary carbocation. So that's why no shifting occurs for that. But it does when it is possible. So what we find, say, for example, a molecule like this, we find that there's very little, 35% yield of the connection of the benzene ring to that primary carbon spot that we thought we were going to attach it to. Instead, 65% is actually attached to this secondary carbon next to the primary carbon. So you have to watch out for rearrangements with Friedel-Crafts alkylation. In addition, we'll end this video. It's a shorter one this week, or this lecture. We'll end it with a few other limitations for Friedel-Crafts alkylation, not acylation. We'll talk about that in lecture, but Friedel-Crafts alkylation. Here's a few more, because if you notice, it involves this SN2, SN1 like mechanisms, these substitution nucleophilic attacks. If you recall, and we've emphasized it now in several different scenarios, sp2 carbons are not great electrophiles for substitution nucleophilic attack type mechanisms, because that carbocation character does not like to form on sp2 carbons. sp2 carbons do not like to bear positive charge. They're less stable carbocations. So you do not find vinylic halides and aryl halides. They do not undergo substitution type reactions, SN2, SN1 like mechanisms. There is one exception, which we're not going to get to except maybe as an extra credit this semester, and that's nucleophilic aromatic substitution. It can be oftentimes confused with EAS, so that's why we kind of we leave it for maybe extra credit material for now. But in these reactions here, you cannot attack a chlorine atom that is connected to sp2 carbons, directly connected to sp2 carbons. So these have no reaction because they're not good even with the AlCl3 catalyst, they're not good electrophiles in other reactions we've seen even, such as the ethers, when we're trying to Williamson ether synthesis. So remember, typical sp2 carbons, poor electrophiles, so a lot of times these mechanisms that involve substitution type reactions, you're not going to see them for those vanillic and aryl halides, sp2 carbons. Another limitation is polyalkylation typically happens. It turns out, we're going to talk about more about this in the next lecture, about reactivity and activation and deactivation of the benzene ring. We're going to find that alkyl groups are what we'll call activating groups. When you begin to attach alkyl groups to a benzene ring, you actually make the benzene ring even more reactive to electrophilic aromatic substitution. Because of that, we tend to find you can't easily, at least, limit your alkylation to one event. It turns out with Friedel-Crafts alkylation, you typically see di and even trialkylation products. In other words, the alkylation attacks the same benzene ring that already had the alkylation occur on it, again for a second and a third even time. So polyalkylation, that is multiple additions of these of this R group, so to speak, substituting for hydrogens, occurs as side products or additional products when doing this reaction, with starting with just normal benzene. So you got to be careful. That's why, I mean, it doesn't mean you still can't do it. In fact, we will find that I will talk about it. And what you assume is that the polyalkylation is a side or minor product, because you will find mostly the monoalkylation product will form. And so we still can use it. It can still be used as a synthetic tool. But it is true that your mono-substituted product, some of it will be lost to becoming either di or tri-substituted. So you do have to watch out for that. The last limitation of Friedel-Crafts alkylation is some groups, once again, as we're going to learn next time in the next lecture, some groups are deactivating groups. So just like alkyl groups activate the benzene ring, as we'll find, and thus we have to worry about polyalkylation, we find that there are some groups, if they're already attached to the benzene ring, they behave as deactivating groups. And as such, it turns out, and this is just a fundamental fact that's going to be tested over and over again about Friedel-Crafts, and this is true for both alkylation and acylation, and that is Friedel-Crafts reactions cannot occur on a benzene ring that's deactivated. Specifically deactivated more deactivated more than bromo or monohalogenated benzene rings. So we're going to find halogens are deactivating, mild deactivating groups, but anything stronger than that, or if there's multiple of those deactivating groups attached, the benzene ring will no longer react in a Friedel-Crafts alkylation and also acylation, as we'll find. So, in other words, if it's too deactivated, no reaction. What's too deactivated? Well, we'll talk more about deactivation specifically in the next lecture, but it's anything more deactivated than a mono halogenated benzene ring. So anything more deactivated than a monohalogenated benzene ring. What is that? We'll learn more about that in the deactivation activating group discussion in the next lecture. For our lecture that goes with this play pause video, we'll now continue our discussion from alkylation to acylation. So when we come in for lecture on Tuesday, we're going to talk about Friedel-Crafts acylation, and then we're also going to talk about there is a way around that whole carbocation rearrangement, and that is using acylation followed by a reduction that we'll learn about that allows us to get some of those primary alkyl groups attached to the benzene with a higher yield, and thus that's the more correct synthetic pathway for problems that involve that it would involve trying to make that substance, whether they be retrosynthesis or something specifically discussing this correction or better pathway to that limitation that is the carbocation rearrangements that occur in Friedel-Crafts alkylation. Anyways, so that's it for this week's for this lecture's PlayPosit. Hope this is good starter and primer for Friedel-Crafts-like reactions. We'll talk more about acylation again in class on Tuesday. I'll see you guys later. Bye.